So let's say you are having some functional f. Okay. So we define functional f to be a mapping from a function to some number. Okay. So this number can be real or complex. Clear? So a functional maps a function to a number. Okay. So that number can be real as or complex. Okay. So what is important for us, it's not just the abstractness of these functions. We are only interested in how to define a derivative of a function with respect to function. In other words, we need to figure out a functional derivative. Clear? So we define this kind of objective. Let's say the variation of f. Okay, so f is a function of some phi. Okay, phi is some function. Let's forget about it's a field. Phi is some function. Okay, and you make a variation with respect to phi of x at some point x. So we will be interested in these kind of objects. So these derivatives will always pop up in field theory. Okay. So this objective tells us how this function varies with respect to the function phi at some point x. Okay. So this x, this point is very important here. Okay. So if I write some another, okay. So we will see in a moment at a given point we will be having many variations of a given function. Okay. You can vary in a different way a given function. Clear? Okay. So we call this as a functional derivative. Huh? Clear? So this variation, okay, so this represents simply the variation of f with respect to some function phi at point x. Okay, so look at the difference. So you can be having, let's say, f of x with respect to x. Let's say this kind of variation. So there is a difference between the two. So it means it is a variation. Okay, so I should put a small f. So it is a variation of some function with respect to the coordinate. Okay? Clear?
Yes, sir.
So how you vary the point? Okay? So that gives you the variation in f. Clear? So here the important is the variation of phi. Okay? So now let me define. Okay, so this functional derivative sometimes, okay, it is also known as Fetcher derivative. Fetched derivative. Okay, so let's put a formal way how to define it. Okay, so suppose if I have to write the variation of this f. Let me write the variation of this f. Okay, so how to write it? Clear? So look here. So phi is a continuous function. Is it? So it depends on the coordinates. Clear? Okay, so before doing this kind of variation, let's take a look at this, the variation of f. Suppose you are having a function f of x1, x2, dash, 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 xn. So this is the function of n coordinates. Clear? Or n variables. Not coordinates, n variables. How I define the variation of this f? Let's say df. How you define it? Okay, so you simply write partial, the variation of function with respect to x1 and multiply dx1 plus dash, 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 and like so. That means it is a linear superposition of all these variations around the given points. So okay, so this is a variation of f about this point x1. Okay, clear? And this is the variation of f around the point xn. Clear? And you are writing this total variation as a linear sum of all these things. So in other words, it goes like this. Let me put as partial f by partial xi, let's say dxi. Clear? So you have to multiply the variation in this coordinate as well. Clear? So now if now this f is a continuous function, okay, and you are having the continuous variables here. In other words, instead of this f, you are having this f. Clear? How you will write now the total variation? What you expected? Yes? Yes, you instead of the variation of this x here, you will put a variation in phi. Clear? So that means you write the variation of this f as a linear sum of all the possible variations at a given point. Clear? Of all the variations at a given point. Clear? Samasha means what? So how you will write? Okay, you will write like this thing. Okay, so let me write this delta f of phi. So I will write it as, let me put this partial f of phi, yes, partial phi of, let's say, x. Clear? So what it gives me? Variations of phi at with respect to phi at some point x. Then what you need to do? You need to multiply variation in phi. Let's write that variation in phi as delta phi of x. Then yes, you need to sum over all these values, okay, at the point x. Clear? So since these are the continuous functions, okay, so these are okay, you can think these are the continuous variables. What I need to do? You need to integrate over this coordinate x. So let's write this as dx. Clear? So and the integration is over the entire domain. Clear? So this is actually the definition of the variation of phi with respect to phi. Okay, so this will serve. Okay, so this will give us the definition of the derivative of this f. Okay, or the definition of a functional derivative. Or in other words, this will be the starting point to define our functional derivatives. Or this itself serves as the definition for the functional derivative. Clear? Got it? Okay. Any question? Okay, so so there is an abuse of notation. So you have to actually, since this is a partial variation, you need to put actually a delta variation, delta like this thing, this delta. But I don't want to confuse you this delta and this thing. So usually you will see in the books delta f here as well, like this thing. You will see like this thing. Sometimes I will be also using the delta f. Okay, then I will not be using this kind of thing. Okay, simply delta. It means a functional derivative. Okay, so this is simply abuse of notation. Okay, so now let's figure out the. Okay, so how we define the derivative? What is the first principle of defining a derivative? So it is limit of epsilon tends to 0, f of x plus epsilon minus f of x. Clear? So we need to make a formal definition of the. Suppose if I am giving you some functional and I ask you to find a derivative, functional derivative, how to do it? Okay, we will simply figure out a rule, then we will do directly. Clear? So this is a first principle. From first principle we always do the derivatives, is it? And you see this epsilon is a localized point around this x, or it is in the neighborhood of x. Since this is in the one dimension, you are having only one point. In that point you are defining a neighborhood, is it? So it means this epsilon is where? It's actually a localized point. Clear? Around this x. Now how to define it? Okay, how to define the functional derivative? What I will do, okay, so what is important here? I need, okay, so if you see here, it is actually the variation of x here, is it? By the infinitesimal amount, okay? Now in function, if you see, so you are having f of phi of x, clear? So what I need to vary? Function itself, okay? Clear? And I have to, in its neighborhood, I have to put a point, an epsilon amount, is it? Infinitesimal point, clear? And then write, let's say, f phi plus the infinitesimal amount minus the f of phi divided by epsilon, clear? And that will define me the derivative, okay? From the first principle. How to do it? What I will choose, let me write this delta phi variation. It will be like this thing, okay? So you can think it like this way. Phi plus some delta phi kind of thing. So this is a variation of phi with where? Around this phi, okay, at some point x, clear? So for that matter, what I will do, let me choose a point, okay, let me choose this delta phi of x, okay, as an infinitesimal variation, okay, localize it at some point y, x is equal to y, clear? So is this a localized point? Because Dirac delta function specifies the point, yeah? So it is non-zero only where? X is equal to y, clear? So that means I am choosing a point y, okay? Sorry, I am choosing a localized point y, clear? Got it? So much. So now let's do it. Let's write this variation. I can write this delta f of phi. So I can define it this way: f of phi plus delta phi minus f of phi. Can I write it? Can I write it? Okay. So now this is by definition equal to, now what this delta phi is by definition equal to? So this is the definition, is it? Okay, let's call this definition as 1. Okay, so this is equal to integral dx like this thing. Clear? Okay. So, or I can write this way. Okay, so let's try. So this is equal to, what is this delta phi equal to? Okay. What is the delta phi of x equal to? So it's epsilon delta x minus y. So that's equal to, so f of phi of x plus epsilon delta of x minus y minus f of phi of x. Okay, so now let's integrate over, okay, so epsilon is a constant number, so let's integrate over x. So x will be replaced by y. So look here, so you are integrating over x, this x will be replaced by y. So this I will put as simply delta f of phi, okay, epsilon times delta of phi of y. Clear? Because I told you this way I am saying it's a functional derivative. Clear? So once you integrate over x, x will be replaced y, then I will write this as delta f by delta phi. Clear? Or in other words, if you see, or I can write this delta f phi by delta f phi of y, so that's equal to limit of epsilon tends to 0. This epsilon will go here, f of phi of x plus epsilon delta of x minus y minus f of phi of x by epsilon. What it is? First principle of, okay? So it is the first principle of the derivative. Clear? You got my point? What is the difference between that? So epsilon you put actually a delta function there. Rest it is the same thing. Okay, so let's take examples. What is the differentiation of x raised power n?
Nx
Huh? Just tell me.
nx n minus n.
Huh? Okay, what is the differentiation of x? Huh? Differentiation of x with respect to x?
1.
Really?
X raised power 0.
Huh? Theta of x, huh? Okay, so it's 1. So let's take our function. Let's take the first case. Okay, so let's write this as simply phi of x. Simple function, eh? So our function is phi of x. Clear? Now let's write the differentiation. So this derivative delta phi of x by delta phi of y. So what that is equal to? Let's use this very rule. Okay. So it is limit of epsilon tends to 0. F of phi plus, okay, what is our f? This phi, clear? So it is phi of x plus epsilon, then delta x minus y. So this is your f of phi plus epsilon delta of x, clear? Then you are adding minus this phi of x divided by epsilon. So what is that equal to? Simply delta x minus y. Now, okay, or in other words, so I am having the functional variation of phi with respect to phi. Okay, so look at the rule. So this is very important rule. So what is okay if it would have been, let's say, delta x by delta x, that is 1, is it? What is differentiation of phi with respect to phi? That should be equal to 1. Clear? Okay, now you are having x here, y here, is it? So what it should, since x and y, these are continuous variables, what you are getting here? Dirac delta function. If it would have been, let's say, like this thing, delta phi I at discrete index, delta j. So if I is equal to j, then it's equal to 1. If I is not equal to j, what it is? 0. So what it would have been? Delta ij. Okay. So now if I put an index here, let me put an index here, a, b. So these are two indices. Okay, discrete indices. Clear? What I should put then in addition? So I'll put in addition delta ab. Clear? Okay, so this will be non-zero only when a is equal to b, otherwise it is 0. Then it would, let's say it would have been, if a is equal to 1, b is equal to 2. So you are having phi 1 differentiating with respect to phi 2. If they are different, then it's equal to 0. Clear? So that's, I have put deliberately here because these kind of derivatives will come often. So you should know. Okay, so now let's take another example. Okay, let's take this integral dx phi raised power n1 x. Clear? Let's take this as an example. Can you tell me what is the result? Okay, there is one important point which I forgot to mention. So the usual rules of differentiation. Okay, what are those? Product rule, quotient rule, is it? Okay, and the chain rule. These follow here as well. You are having the same as well. I will not write the product rule and quotient rule. I'll give you the chain rule in a moment. But let's try to differentiate this thing. Okay, let's have a functional derivative of this very object. So what I am having? So it is delta f of phi by delta phi of y. Okay, so that's equal to limit of epsilon tends to 0. Clear? So what you are having? So you put dx, then phi plus epsilon delta. Clear? Is that true? Okay, so what you are having? Phi raised for n, let me put x plus epsilon delta x minus y raised for minus integral, because the power n is only over phi. Clear? That's why you have to put power only over this object. So these are the simple things, you know. Like this thing divided by epsilon. So what this will be? Okay, so now let's look. So first term will be phi raised for n, is it? So that will cancel with this very term. Clear? Now second term will be n epsilon. Okay, delta of x minus y, phi raised for n minus 1. Clear? Okay, so epsilon and epsilon will go, and the other terms will be having epsilon there. Clear? So just make a binomial extension of this thing. So what you will get? The first term you will be having a raised for n. Second term, okay, a plus b raised for n is what? A raised for n plus n, a raised for n minus 1, b plus so on. All other terms plus b raised for n. Clear? Samajh? Now look here. A raised for n will cancel with this object. Clear? And another term is n epsilon, a raised for n minus 1 and b. Clear? So epsilon and epsilon, because you are having only linear order. Other terms will be having epsilon square, epsilon cube, and so on, epsilon raised for n. Is it? So when you take epsilon tends to 0, so those will cancel out. Okay. So what remains here? So it will be simply dx. Okay, epsilon n. Then just tell me phi raised for n minus 1 of x and delta x minus y. So what you get? Sorry, epsilon and epsilon goes.
Yes, sir.
So it will be simply phi n raised for minus 1 y. When you integrate over x, you will get y. Now look here. What is the variable you are getting here? So what you are having? So the variable with respect you are making a differentiation. Okay, so you will get that variable on the right hand side. Clear? So remember this objective. Okay? So because what is the free index? It's y is a free index here. Eh? Look, f is the implicit function of x here. It's not an explicit function of x. Clear? F is a function of phi, not x. Huh? Okay, but here this phi is an explicit function of y. Huh? So you take this y as an independent variable. Clear? Rather you can take it as a free variable and it will appear here. So free variables have to be balanced in a given equation. Clear? Everybody got it? Okay. So let me put a chain rule quickly, then we'll go to okay. So how we define the chain rule? Anybody? Suppose so you are having df by dx. You write the chain rule how? Let's say partial f by partial t and partial t by partial x plus other terms. Clear? So this is how you define the chain rule. If this, let's say, there is a dependence on other variables as well, so you make this kind of chain rule. How to define a chain rule here? Clear? So let's write it. So you are having f phi by phi of y. Let's say I will be using y, okay, because I will reserve x for something else. So how to do it? So it will be variation in f. Okay, let's say you are making a chain rule with okay, you are having another function there g. So I will write g of so let me put phi, let's say g of x and delta g of x the same way, huh? And then what you are having? Delta phi of y. Okay, then what you have to do? X is a continuous variable, is it? You have to sum over all these variables. What you need to do? You put a integration over the variable on which you are doing a chain rule. Clear? Clear? Oh, sorry. Is it okay? Yes, it's okay. There is no problem. Okay, so it is okay. Clear? So this is how we define it. Okay, so now let's go to physics back. I mean, what we had done yesterday. So let's go there. So this is how we define the functional derivatives and so on. Clear? Okay. So let's move towards what we had done yesterday. We have defined actually the Lagrangian. Clear? Okay? Yes, bataiye. Any question? All of you are satisfied with what I have done? Okay, good. So we have defined yesterday action. Okay? It's a it's a functional. So of this Lagrangian phi of x. Okay, partial mu phi of x. And this Lagrangian is actually, it is not simple Lagrangian, it's a density. Clear? Now I need to calculate. Okay, if I know phi. Okay, and I have told you phi you can think as some coordinate. Clear? So if I know the coordinate of a certain particle, I should be able to know. Okay, if I know the coordinate as well as the Lagrangian, I should be able to figure out the generalized momentum, is it? Or the momentum of the particle in order to figure out the energy. Hamiltonian. Clear? Now I know here phi. Phi is some variable. Clear? And corresponding to phi, I should be able to define a canonical momentum. Clear? So, since this Lagrangian is simply a mathematical function represent, it's an energy function. Okay, let's try to figure out what is the amount of energy stored in field phi. Clear? So we are having field phi. For that we have written the Lagrangian density, and I need to figure out what is the amount of energy that is stored there. Clear? For that matter, I have to figure out what is the Hamiltonian. Is it? So, before calculating the Hamiltonian, I will figure out first the Hamiltonian density. So by making a Legendre transformation. For that matter, what I need to do? I need to figure out the generalized momentum or the momentum density, or in other words, I need to figure out the Legendre map. Okay. So what I will do, I will define the canonical conjugate momentum. Okay. It will be now momentum density. Clear? Like this way. So let me define this pi. It is as a momentum density. It is the functional derivative of L with respect to phi dot. Okay. Phi dot is the time derivative of what? Phi. So, or in other words, I can write it. Okay. So this is also written like this way: partial L by partial 0 phi, and this object is what? Phi dot. Clear? So now, since you are having a density here, so what you will get? Density on the right hand side as well. Clear? Now what is, okay, so if you are having, if you can write these phi dots and phi in terms of, if this map is invertible, then I can define the energy. Clear? Okay. Everybody has followed it? Okay. Okay, so how I define now the Hamilton? So I am having now Hamiltonian density. So that I write as H. So you are having pi, then phi dot minus Lagrangian density. Okay, and we calculate therefore total energy. So that is simply equal to H integration over the volume of this. So what is that equal to? d3 of x pi. Okay, so we will take the examples first and then we'll proceed. Okay? This is how we define. Okay, so let's take an example quickly. Okay, so let's take the scalar field. Real scalar field. Okay. So what is the Lagrangian here? Half of, yesterday we wrote it, partial mu phi minus half of m square phi square. Clear? So now let's write the canonical momentum pi. So what it will be? Partial L by partial phi dot. Is it? Or partial L by partial 0 phi. Clear? समझ आओ? So which terms contains the derivatives? Just tell me. So this contains the derivatives, time derivative as well as the space derivative. Okay. So but I need to calculate with respect to time derivative. Okay. So with respect to phi dot, I have to calculate this partial L by partial phi dot. Okay. So how to do it? So you can simply write it how? So it will be differentiation of this thing, and mu will be equal to 0. Clear? So or if you are not able to do it, so just write it in the write it as a term wise. Time derivative you just separate out the time derivative and space derivative. Since mu goes from 0 to 3, so you can write it as like this thing. So it will be phi 0. Okay, let me write for you people. Okay, plus partial I phi partial I. So what that is equal to? So that's equal to half of. So this is phi dot. So it will be phi dot square. So what? Can anybody tell me what this is? It's minus. So this will be del nabla phi, and this will be minus nabla phi. Yeah? So that's why you are having minus. Clear? Got it? Okay. If you remember, we are having this partial mu as partial t and nabla. And you are having this partial mu as partial t and minus. That's right. Now let's make a derivative of partial L by partial phi dot. So this will be contributing. Clear? So what you will get? 2. So you will be simply getting phi dot. Okay? Got it? समझ आओ? So now let's write the Hamiltonian. So therefore the Hamiltonian, let's write the Hamiltonian density, this fancy H. So it is pi phi dot minus L. So what is phi? It's phi dot. So you will be getting phi dot, then phi dot, okay, minus L. What is L now? It is half of, okay, phi dot square minus nebula phi square, okay. Then you are having minus half square, minus and minus is plus. Half m square phi square. Clear? So what is that equal to? So this is 1 minus half, it is half. So it is half of phi dot square plus half. So I will take half out. Delta phi square plus m square phi square. Clear? So this is the energy density contained in the field phi. Clear? So let's write now the total energy. So total energy is simply the integration over volume. So you can write now the energy. So that is H is equal to integration dx of that. So it will be half outside. So you are having phi dot square. What is phi dot? That's pi. Yeah? So let's write it as a pi because we have to put it in terms of momentum. So it will be simply pi square plus delta phi square plus m square phi square. So this is the energy density contained in the energy, total energy in a field phi, scalar field phi. Clear? So this is simply the classical energy. It is we are calculating these for the classical fields. There is nothing quantum. Clear? Okay. So everybody has followed it. Okay. So now let's define. So if I have defined the Hamiltonian, now I should be actually able to define the Poisson bracket. Clear? Okay. So now let's define the Poisson bracket. So let's define Poisson bracket for f1 and f2, some two function these variables. So how you define it? Let's say there are n coordinates. You define it summation over I, partial f1 by partial qi, and partial f2 by partial pi minus partial f1 by partial pi and partial f2 by partial. So this is how you define the Poisson bracket. Clear? Now instead of functions, what you are having? Functionals. Okay, so how I define? So let's say you are having two functionals, f1 and f2. So these are two functionals. So you have to define the Poisson bracket. Okay, now look simple. So what is the index that is summed over? I. There is an index I. It's a discrete index. Now if I go to the continuum fashion, in the continuum limit, so what this summation will go? As an integration. Clear? Okay. So let's put it as integration. So let's call that variable as z. So dz. Okay? So I am saying this I goes to a variable z. So it is an integrating variable, dummy variable. So what you have to write? Instead of delta f1, so I will write, partial f1 you will write delta f1 by delta q. What is the analog of the q in fields? It's phi. Phi is a field itself. If you know the field, okay, for that matter you write phi. What will be the variable? Z. So this I will be z. Okay, then you put a variation of f2 with respect to the momentum. That is pi. Let's write it as z. Clear? समझ आया? Everybody followed it? Okay. So minus delta f1 by delta. Okay, so there is one subtlety. So I will tell you in a moment. So these are all three-dimensional variables. Since I am taking it in one dimension,
delta pi.
Okay, so let's write. It is pi z delta f2 by delta phi of z. Okay, so this is simply one-dimensional variables I am taking. Okay, z is a one-dimensional variable. Okay, clear? It is. You can think these are fields in one dimension. There isn't any problem. Okay. Now one important point is that, so in defining this Poisson bracket, I have assumed time of this function and time of this, okay, time argument of this function and time argument of this function, they are same. In other words, I have defined this Poisson bracket at equal times, not at on unequal times. Clear? So much for that, I have not considered time anywhere, is it? But once we will take commutators, we will be defining commutators at equal times. Clear? So much for, since it is simply a mathematical function here, okay, to simplify things, I will not consider time. Once that part comes, I will tell you why we need to take time at equal times and why not the unequal times. Clear? Okay, so for the timing, let's forget about time. Okay, let's take an example. So let's calculate the Poisson bracket of this f phi of x. F1 is phi of x and another is what? Phi of y. Clear? Got it? So what is the argument? X and y. Okay, so I am not considering here more than one dimension. It is, if you take it 3 dimensions, then it will be x vector, y vector. It will be integration over there, d3z over a volume. So much. So generalization is simple. Okay, so let's write it. Integration over z. So then what you are having? Partial f1 by, so that is partial phi of x by partial phi of z. Sorry, delta, not partial. Delta pi of y, delta pi of z, minus delta phi of x, delta pi of z, delta pi of y, delta phi of z. Clear? So everybody got it? Everybody got it what I have done? Simply, what is f1 and f2? f1 is phi, f2 is pi. And simply replace this f by, okay, so the argument is here x and here it is y and you are integrating over z. Now tell me, what is differentiation of phi with respect to pi? Both are different, is it? So it is 0. So that means this object is 0. This object is as well 0. Clear? So now tell me what this object is. Anybody? So it will be simply delta x minus z. What this will be? Delta y minus z. Got it? Okay, so now if I integrate over z, call one delta as a function, another as a delta function. Clear? So you integrate over z, this z will be replaced by y here, or this z will be replaced by x. Clear? So it's one and the same thing. So okay, so it's like this. So what you got, so it is integration over z, delta of x minus z, delta y minus z. So integrate over z, this z will be replaced by y, or this z will be replaced by x, and one delta is gone. So it will be simply delta x minus y. Now look at the Poisson factor. So it is delta function, not 1. Although it's an identity. Now here you are dealing with the continuous variables. Okay, so now let's do this way. So if you are having qi and pj, Poisson bracket, what you will get? Delta ij. Clear? So when I is equal to j, it is equal to 1. When I is not equal to j, it is equal to 0. The same thing. I and j goes as a continuous variable, phi of x and pi of x. Clear? So this is how we calculate the Poisson brackets. Clear? Any question? Any problem? So you can similarly define one important equation, that is Hamilton-Jacobi equation, but we will not be dealing with that. Okay, that equation. So is any time remaining? Okay. Now how we know what is the form of a Lagrangian? Okay, let's try to figure out what is the Lagrangian of a free particle. This has been done. You know from your classical mechanics. So the Lagrangian of a system of particles are simple particles. You write it as kinetic energy minus potential energy. Now let's take the free particle. What is the Lagrangian? So it will be kinetic energy, that is half of mv square, potential energy is 0, so it is simply half of mv square. Now the point is that how you arrived it. So you can simply derive it from the Newton's equation of motion, okay? Simple Newton's law, or you can do the D'Alembert's principle in classical mechanics, and you arrive at this kind of form. And you know what is the kinetic energy of a particle, what are the potential energies, you do the same manipulation, you get these kind of functions, okay? Now, but what is the basic principle? We need to understand what is a basic principle in formulating, okay, a Lagrangian. Suppose if I am giving a field, and let's say some scalar field, and I am saying construct the Lagrangian for it. How you can construct? Okay, you need to construct the Lagrangian, is it? What is a basic principle to construct the Lagrangian? No. Okay? So we need to figure out what kind of considerations we need to take into account. Okay? The foundational principle of physics is the symmetries. One of the foundational principles are what? You invoke symmetries in a given system. What kind of symmetry it follows? Based on those kind of symmetries, you arrive at a Lagrangian. Okay? So let's try to construct the Lagrangian of a free particle based on symmetries. Okay? Clear? Okay. So if you are having a free particle, how you construct the Lagrangian? Okay, so what is the Lagrangian? Is a function of q and q dot. Clear? So this is we know Lagrangian is a function of q and q dot. Okay, now how to construct the Lagrangian of a free particle? Suppose if I don't know the kinetic energy, how to construct it? So what are the basic principles, symmetry principles for a free particle? Okay, so what are the basic principles of mechanics? Conservation principles, is it? So what are those? The conservation of the linear momentum, conservation of angular momentum, and conservation of energy, is it? So where from these conservation laws arise? Linear momentum comes from where? Homogeneity of space, is it? Clear? And where from conservation of energy comes from? Homogeneity of time. So the motion is homogeneous in time, motion is homogeneous in space, and isotropy of space yields you the conservation of angular momentum. Clear? Okay, so now applying these principles, if I am having, let's say, your space is homogeneous, is it? So what it would imply? Suppose if I have to construct a function which follows all these three conservation laws or all three symmetries, what kind of function I need? I need a scalar function first. At very first instant, I need a scalar function because it is only the scalar function which will remain invariant under what? It will remain invariant under rotation, translation, as well as time translation. Is it? Clear? So all these three symmetries will be followed by scalar quantities. So let's call that scalar quantity as L. Okay? Now, and I am saying this scalar quantity depends on Q and Q dot. Clear? Okay, so what kind of function it should be? So shall it depend on a vector Q dot? Suppose if I am having a scalar function, okay, shall it depend on a vector Q and vector Q dot or any other thing? So if L is a scalar function, it should come from the scalar quantities, is it? So what is the basic scalar quantity? A dot product. Clear? If I don't have a dot product at all, let's say if this is a vector quantity like this way, it says some vector Q, some vector Q dot, and so on. Clear? Or these invariant vectors will transform under a certain kind of transformation. Is it? Summation, what I need to do? I have to construct a scalar quantity. Summation? Okay, so what kind of scalar quantity I need to construct it? So it will be Q square. So that is actually Q dot from dot product. Similarly, this Q dot dot Q dot. Okay? So that means this Lagrangian should be actually the function of, okay, q square, q dot square, q4, q dot 4, and so on. All the higher powers. Okay? Odd powers will not come because you that will violate these symmetry principles. Okay, the first argument, it should not depend on the position square. For a free particle, it should not depend upon the position square. Why? Why it should not depend on, let's say, for a free particle, why it should not depend on the position? This energy function, this L, why it should not depend on the position square? On the position, square of the position.
It's homogeneous.
Yes?
Homogeneous space.
Hmm?
It will give us only positive values.
What is the condition it will violate?
Homogeneous space.
Huh? Translation. Yes. So one that is the thing. So q square will violate the translation. So it will not be invariant, because if you take, let's say, q to q plus a, so what will be q square? So there will be what? You will be having q square plus a square term, a constant term will pop up. Okay? Clear? So now you can ignore the coordinates. So it should only depend upon the powers, even powers of this q dot square. Clear? Samajh aa? You got my point? So we are using symmetry principle. So that means, so this should actually now depend on what? Q dot square, q dot raised power 4, and so on. Okay? So that means this Lagrangian for a free particle should only depend upon squares of these velocities, not on the coordinates. Clear? Okay. So now tell me, okay, so q dot square is what? Q dot square gives me velocity square, is it? Okay, I am saying it will only depend on velocity square. It will not depend upon the higher powers. Let's say velocity 4, velocity 6, and so on. Clear? Are you getting my point? It will not depend on. Why? The reason being, once you, okay, so there is a relativity principle in classical physics. What is that? Galilean relativity, is it? Okay, so the scalar functions be invariant. Clear? Since Lagrangian, you can define up to a freedom, what we call a gauge freedom, is it? Okay, so if you remember, so the action, if you define it as L dt, so this will be same as L plus df by dt. Okay, let's say some g, because I'm using f here, provided this g vanishes at boundary. Okay, because it's a total time derivative, you can always add a total time derivative. Okay, now if you apply the Galilean transformation, let's say if you are having a function that is only dependent on q dot square, it will be invariant under Galilean transformation up to this kind of function. Clear? But if you add q dot raised power 4, this will not give you the Galilean invariance of the action. Clear? So, samajh aa? So higher powers of the velocities, higher powers more than 2 will not give you the correct description under Galilean transformations. Clear? So, samajh aa? Because we are doing a non-relativistic free particle. Okay, so that means this Lagrangian should be simply proportional to what? Q dot square. Clear? So what is the kinetic energy of the free particle? Huh? Half of mv square. So you remove the proportionality constant, you get. Okay, so this proportionality constant is adjusted from the Newton's equation of motion. Okay? So you cannot fix these proportionality constants arbitrarily, because you need to check in which domain what kind of law governs the dynamics. So that law will fix up these constants. Let's say if you are writing the Newton's equation of motion, what is the Newton's equation of motion for a free particle? It's mx double dot is equal to 0, is it? And we know from Lagrangian we can write the Euler-Lagrange equations and we can calculate the equations of motion. Okay, the Newton's law. Clear? And if you integrate that, what you will get? You get actually what? Okay, so Okay, if you form this Lagrangian, you need to calculate the equation of motion. What you will get? Q dot square will go as Q double dot with twice. Clear? And that 2 and 2 will cancel. So you will get MQ double dot is equal to 0. Okay? So this 2 is just here what? And M by 2 is simply because M is an inertial property, is it? So if you are having a material particle, those follows actually Newton's laws, and those are based on the inertia, inertial property, and you have to multiply that kind of constant here. Okay? समझ आओ? So you are having this Lagrangian to be now M by 2 V square. So where from we have constructed it? From the symmetry arguments. Okay? Clear?
Yes, sir.
समझ आओ? Now we need to fill. Okay, so there is a. Okay, so if you are having some theory at hand, or you are having some field now, and I ask you to construct a Lagrangian for that field, you will check what kind of properties this field satisfies. Okay, based on those arguments, or in other words, based on the symmetry principles, we can construct what? A Lagrangian or Lagrangian density for that kind of field. Okay, समझ आओ? Okay, there is a theorem which describes the connection between continuous symmetries and the conservation laws, because we have come from here, from a conservation law, and we said there is a conservation of momentum, conservation of angular momentum, and conservation of energy, and they have come from where? Actually the symmetry principles, is it? A translation symmetry is a continuous symmetry, time translation is a continuous symmetry, is it? Those yield you the conservation of energy and momentum, is it? And rotational symmetry is what? It's a continuous symmetry, it gives you the conservation of the angular momentum. So that means there is a connection between a symmetry and a conservation law. I should say there is a connection between a continuous symmetry and a conservation law. This is the statement of the Noether theorem. Noether theorem says, okay, it is due to M. Noether, okay, so it says for every continuous symmetry there exists a conservation law. Okay? Okay? Got it? So it says, so you are having for every continuous symmetry, in other words, I will write it in this fashion. You are having a continuous symmetry, so it implies this way a conservation law. So if you are having a conservation law, it means there exists a continuous symmetry, or if you are having a continuous symmetry, it implies a conservation law. So this is the content of the Noether theorem. We are going to prove it probably anytime. I mean, so in the next lecture. Clear? So let's stop.